Welcome to ZK Vibes, your go-to podcast for all things zero knowledge. Today we're diving into a really fascinating frontier, right at the intersection of cryptography and machine learning. We're calling it AI You Can Prove. Think about how much you rely on AI every single day, getting recommendations, asking complex questions. But what if you had to rely on its output for something truly critical, like, say, a medical diagnosis or maybe a loan application that affects your entire future? How much do you really trust that little black box to get it right every single time?
That's a huge question, isn't it? Especially as AI gets, baked into these really high stakes areas. Right now, our trust often comes down to, trust. We're told to rely on an AI because it's from a reputable company or a known institution.
But that's trust based on policy, right? Or a brand name. It's not actual technical proof. And when the stakes are really high, just hearing trust us doesn't feel like quite enough.
Exactly. And trying to verify an AI's output yourself, historically, that's been incredibly difficult. You might need access to the model's inner workings, its parameters.
Which is a huge risk for the company that built it, exposing sensitive IP.
Absolutely. Or the methods themselves are just so technically complex, they're basically out of reach for, most people or organizations.
So we need something fundamentally different, a new approach.
We really do. The shift that's needed is away from this centralized, institution-driven kind of assurance towards something more global, auditable, neutral, and really technical. A foundation built on cryptographic guarantees.
Proofs you can check yourself.
Proofs you can verify independently, yeah. Not just taking someone's word for it.
And that's really the heart of what we're digging into today. This intersection where crypto provides verifiable truth for AI you can prove. And specifically, we're going to look at a framework designed for this. Lagrange's Deep Prove. That launched back in March 2025.
Yeah, and our mission for this deep dive is really to unpack how this tech actually works, sort of under the hood. Understand why this kind of verifiable AI is becoming so crucial right now, and maybe explore what it all means for building a more trustworthy future with AI.
Okay, so let's get into that trust deficit you mentioned earlier. We interact with these AI models all the time, LLMs, diagnostic tools, financial algorithms, and they often feel like black boxes, don't they?
Totally. You give it an input, you get an output. But the why? That's often hidden. You might not know why it gave that specific result, or even if it was running the correct, untampered version of the model.
Right. And as you said, the old ways of trying to check, asking for the model's secrets or expecting users to run complex crypto checks just don't scale.
They're non-starters, really. Companies need to protect their IP, and end users can't become crypto experts overnight.
Which perfectly frames this paradigm shift needed. Moving from trust us, we're company X, to
you can mathematically prove this result is correct for this model and this input because the cryptography says so.
Yeah.
It needs to be this neutral, verifiable layer that anyone can use.
Okay, so enter Deep Proof, Lagrange's solution. You described it as a zero-knowledge machine learning ZKML inference framework.
That's right, ZKML. Its main job is to take the output of a neural network and generate a cryptographic proof for that specific output.
So let's break that down. If I have my input, X, and the AI gives me an output, Y Deep Proof creates a proof that basically says, yep, Y is definitely the correct result from running this specific model on that specific X.
That's the essence of it, yes. And here's a really clever part, the zero-knowledge aspect. It provides this verification without revealing the sensitive stuff.
Ah, okay. So the proof verifies correctness.
While keeping the model's internal structure, the weights, private, and just as importantly, it doesn't reveal the original input data, X, during the verification process itself.
That's the dual benefit then, verifiability and privacy. That sounds pretty significant.
It's huge. It unlocks use cases where you need proof but can't afford to leak data or IP.
And the source material mentions some pretty eye-popping performance claims too. Like, this isn't just theory, it's aimed at being practical.
It certainly seems that way. They claim, compared to some baseline, proof generation speeds up to 1,000x faster, verification up to 671x faster, and the initial setup, which is a one-time thing, up to 1150x faster.
Wow. Okay, those are serious speedups. If those hold up in real-world use, that makes ZK for AI much more feasible.
Definitely indicates a strong focus on efficiency and usability.
All right, let's peek under the hood a little bit then. What's the crypto magic making this work? The source mentioned a couple of key techniques.
Yeah, the two main ones highlighted are the sum-check protocol and lookup arguments, both adapted for, the kind of math that happens inside neural networks.
Sum-check protocol. What's the gist of that?
So think of sum-check generally as a really efficient interactive proof. One side convinces the other that a complex sum calculated over polynomials, is correct. Crucially, it does this without revealing all the individual values that were summed up, or the full polynomial details. It's about efficiency and privacy.
And how does that map onto AI calculations? Neural networks involve a lot of matrix math, right?
Exactly. A lot of the computation in neural networks is linear matrix multiplications, convolutions. DeepProof cleverly adapts SumCheck to handle these. Essentially, it reframes that linear algebra as polynomial computations. Then SumCheck can verify those computations super efficiently, and again, without needing to see the actual data flowing through.
Okay, so that covers the linear heavy lifting efficiently and privately. But neural networks aren't just linear, are they? They have activation functions like ReLU, softmax, nonlinear steps.
Right. And those nonlinear bits are trickier for polynomial-based proofs like SumCheck. That's where lookup arguments come into play.
Lookup arguments, how do they work?
They're kind of a clever shortcut. Instead of trying to prove the complex nonlinear math directly each time, which can be slow, the system pre-computes all the possible valid input-output pairs for a specific nonlinear function, like ReLU, and stores them in a table.
Like a pre-approved list.
Exactly. Then, the lookup argument just needs to prove that the actual output the model computed during inference is present in that pre-computed table of valid outputs.
Ah, so it's proving this result is on the list of allowed results for this step, not proving the calculation itself.
Precisely. It's much faster for common nonlinearities. It checks membership in a set rather than redoing the complex math proof. It significantly speeds up proof generation.
Makes sense. Using the right tool for the job, SumCheck for linear, lookups for nonlinear. Okay, so those are the crypto building blocks. Let's walk through the workflow. If I'm a developer, how do I use DeepProof? Step by step.
Right. The workflow described starts with step 1, pre-processing. This is a one-time setup you do for each trained model you want to make verifiable.
One time per model.
Okay. You take your trained model, usually exported in the ONNX format, which is a pretty standard way to share models.
ONNX, yeah, I've seen that.
And you provide some sample inputs. DeepProof then parses the model structure, gets it ready for the ZK system that involves quantization, making the numbers work well in the proof system, and it generates the specific crypto keys needed, the prover keys and the verifier keys.
And the key thing is, this is just done once.
Exactly. Once you've done this setup for a specific model version, you don't need to repeat it.
Got it. Setup done. Now, what if I want to actually prove an inference? I have a new input.
That brings us to step 2, proving. You take your new input, let's call it X again, you feed it to DeepProof. DeepProof runs the model on X just like a normal inference pass. But while it's doing that, it meticulously records the execution trace.
The execution trace. Like a log of everything that happened computationally.
Sort of, yeah. It tracks how the data flowed and transformed to every single node or layer in the neural network. A detailed computational journey. Using this trace, DeepProof then generates small, individual cryptographic proofs for the computation done at each node.
Proofs for every little step.
Yep. And then it aggregates all those tiny proofs together into one single, compact, final proof. This final proof covers the correctness of the entire model's execution for that input X.
Aggregation is key for keeping it manageable, I imagine. Okay, so now I have my input X, my output Y, and this succinct proof. What's the last step?
Step 3, verification. And this is where the beauty of ZK really shines. To verify, you don't need the original model's weights or anything secret.
What do you need then?
You need the input X and the output Y that are being claimed. You also need a commitment to the model.
A commitment, like a fingerprint.
Exactly, like a cryptographic fingerprint. It proves which model was used without revealing its internals, and you need the verification keys that were generated back in step 1, the pre-processing.
Okay, input, output, model fingerprint, and verification keys.
Right. Anyone can take these pieces, run the verification algorithm using the proof generated in step 2, and they get a simple yes-no answer. Is it true that this output Y came from running this specific model, identified by the commitment, on this specific input X?
And crucially, the verifier learns nothing else. Not the model weights, not necessarily anything sensitive about the input X beyond what's maybe obvious from Y.
Precisely. Verification confirms correctness while preserving privacy.
So, boiling it down for a developer. Export to own an X, one-time pre-process strapped, generate proof per inference. Anyone can verify publicly. That sounds pretty streamlined, actually.
It's designed to integrate into existing ML workflows.
Yeah.
But there's always a but. with the ZK, isn't there? Generating those proofs, especially step 2.
It's computationally expensive.
Yeah, that's the classic ZK challenge.
Yeah.
Running a big AI model and generating a proof for it sounds like it needs serious horsepower.
It absolutely does.
Yeah.
And that's the next piece of the puzzle. How do you make that intensive proof generation practical? How do you scale it so it's not a bottleneck?
Right. You can't expect every developer or verifier to have like a supercomputer cluster handy just for generating proofs.
No, definitely not. And this is where Lagrange brings in its other major component, the Lagrange Prover Network, or LPN. dprove essentially offloads the hard work of proof generation to this network.
Okay, tell me about the LPN. What is it? Think of the LPN as a decentralized cloud, basically. A distributed network made up of specialized nodes, they call them provers. These provers have the hardware and software optimized specifically for generating zero-knowledge proofs quickly and efficiently. They do the heavy computational lifting.
So it's like crowdsourcing the proof computation.
In a sense, yeah. It distributes the workload across many specialized machines instead of relying on one central powerful server.
What are the benefits of that structure?
Well, several. It avoids single points of failure. It prevents bottlenecks. If one prover is busy, others can take the load. It should naturally drive down the cost per proof through competition and economies of scale. And it maintains decentralization, which is often a core goal in these systems. Plus, provers can even specialize, maybe optimizing their hardware for specific types of AI models or proof systems.
Okay, so how does dprove specifically use this LPN when I ask for a proof for my AI model?
It's quite clever. dprove can actually take the large computation of running an AI model and break it down into smaller pieces.
Parallelize the proving.
Exactly. It sends these smaller computational chunks out to different provers on the LPN, potentially many working in parallel. Each prover computes the proof for its little piece. Then, the network aggregates these partial proofs back together into the single, final, compact proof for the entire inference.
That sounds much more efficient. Distributed parallel proof generation.
Yeah. And they also mention a specialized layer within the LPN specifically for these EKLML workloads.
Yep.
This means provers in that layer can really optimize their hardware think GPUs, maybe even ASICs down the line, specifically for the kinds of math AI needs, making proofs for AI even faster and cheaper.
Okay, so the LPN provides the muscle.
Yeah.
But how does it all work economically? How does the network decide who gets which proving job? And how do the provers get paid for their work? Must be some mechanism there.
There is. It's called DRA, the Double Auction Resource Allocation Mechanism.
ER. Sounds complex.
The core idea is actually like a marketplace. It matches people who need proofs generated to clients or requesters with the provers on the LPN who can actually do the computation. It's described as a double auction, meaning both sides participate.
So clients bid what they're willing to pay, and provers bid based on their costs.
Essentially, yes. DRA uses an algorithm. They mention it's knapsack-based, which is a classic optimization approach to find the best matches. It tries to maximize the overall value, pairing high-value requests with capable, cost-effective provers.
How does it keep everyone honest, prevent price gouging or lowballing?
It uses what's called a threshold pricing model. Basically, clients pay just enough to win their bid against the next best alternative. This encourages them to bid their true value. And provers get paid a competitive rate based on the auction outcome. The goal is an efficient, fair marketplace that isn't extractive for either side.
Makes sense. You need a sustainable economic model for a decentralized network like this. And where does the token, the LI token, fit in?
The LEDA token is central to the LPN's economy. It's the native currency for compensation. Clients might pay their fees using various crypto assets, ETH, USDC, maybe LELA itself. But the provers, the ones doing the computational work,
They always get paid in LELA.
they are always compensated in LEDA tokens. That's the reward for their service.
Okay, so LELA fuels the prover side of the network.
Exactly. And the source mentions there's a fixed 4% annual emission of new LELA tokens. This emission seems to serve two main purposes. One, it helps subsidize the cost for clients, making proof generation more affordable. Two, it provides a steady stream of rewards for the provers, incentivizing them to participate and process proofs.
And can token holders get involved?
Yes, the mechanism allows LELA token holders to stake or delegate their tokens to specific provers they want to support. This likely helps secure the network, maybe influences which provers get more work, and potentially earns rewards for the stakers delegators.
Okay, so wrapping that section up. dprove provides the ZK framework for AI. The LPN provides the scalable, decentralized computation. And DIR with the LELA token provides the economic engine to make it all run. Seems like a complete system design.
That seems to be the goal, yes. To create this whole ecosystem where the high cost of ZK-proof generation is managed effectively, making those cryptographic guarantees widely usable for AI.
All right. We've gone deep into the tech, the network, the economics. Let's pull back up to the big picture. Why should you, our listener, really care about this idea of AI you can prove? What difference does it make in the real world?
Well, it fundamentally changes the game for trust in AI, doesn't it?
Yeah.
It shifts us away from just having faith in a brand or an institution towards having actual verifiable mathematical certainty about an AI's output. It embodies that idea. Don't just trust AI, verify it.
Let's think about those examples from the source material again. A hospital using AI to analyze medical images. With something like Deep Proof, they could potentially get a proof confirming the AI's finding was correctly generated by the approved model.
Without ever having to send the sensitive patient scan data outside their secure environment for someone else to check. The proof travels, not the private data.
Or the bank using AI for loan decisions. Imagine getting a proof that shows the decision was made according to the bank's stated fair lending model, using your data correctly.
Exactly. It helps ensure fairness and transparency. Again, without exposing all your private financial details during the verification process.
What about deep fakes? This seems like a powerful tool there.
Potentially, yes. Instead of just subjective analysis, you might get a cryptographic proof stating whether a piece of media was or wasn't generated by a known AI model, or even just basic trust in everyday interactions. How do you know the chatbot you're talking to is running the genuine intended model and not some altered or malicious version? A proof could verify that.
These are all areas where trust is crucial, but verification has been really hard or involved major privacy trade-offs.
Right. Deep Proof, by combining ZKML for the privacy-preserving proofs and the LPN for making it scalable, aims to make these kinds of critical applications practical.
It really feels like building a foundational layer of trust based on math, not just promises.
That's the potential, yeah. A technical foundation for trust in an increasingly AI-powered world.
So here's a final thought to leave you with. If we can use cryptography to bring this kind of technical proof, this verifiability, to something as complex and often opaque as AI, what other complex systems in our lives, systems where trust is essential but hard to verify, could benefit from this kind of approach? Where else could we move from just trusting to actually verifying? Something to ponder.
Absolutely. Well, we've taken quite the deep dive today into Lagrange's Deep Proof, exploring how zero-knowledge proofs and the Lagrange prover network aim to make AI verifiable and private, addressing that really critical need for trust in these powerful systems.
It's been a fascinating exploration. Thanks for breaking it down.
My pleasure. Always exciting to see crypto tackling these big challenges.
If you enjoyed the show, follow us on ZK Vibes Twitter to stay updated on new episodes, guests, and the latest ZK breakthroughs.
Until next time, stay curious and stay zero knowledge.